Hello everyone, here's a video on the energetics of making solutions. So I don't know if you've ever wondered, but every once in a while when we mix up chemicals, they either get really hot or really cold or slightly hot, slightly cold, but the temperature changes. There's a reason for that, and it has to do with bond breaking and bond making like we've talked about before. So anytime you make a solution, you have to consider three things. First of all, you have to break apart the stuff you're dissolving, the solute. So you have to tear that apart, okay? So that's bond breaking. So if bond breaking, remember that's endothermic, so I'm going to put energy in to break those bonds. And then the next thing you got to do is break apart if this is an aqueous solution, you're going to break apart the water molecules. Those have to split. So again, you have to break those intermolecular forces of attraction. That's another endothermic thing. And finally, the two are going to come together and interact, probably electrostatically. And if that's the case, you are definitely going to be exothermic. So in the case of sodium hydroxide, mixing with water, you have to break apart this, that's endothermic. Then you have, now that you have this and this, those ions, then you have to break apart the water-water attractions. That's also endothermic. And then the actual mixing of the ions with the water is extremely exothermic. With being so exothermic, this stuff gets really, really hot, okay? So with these three together, it's not like, it's not like a checklist, like one thing happens. It's a concerted process. It happens all at once, and the result is very exothermic. So let's go through a couple of these things here. So when we talk about heat to solution, um, in other words, when ethanol is dissolved in water, the delta H for this heat of solution is negative 10.7 kilojoules per mole, okay? Now, the reason is because we're having, notice it's exothermic, and so this is the energetics we're talking about here. So when this happens, it kicks out or is negative 10.7 kilojoules of heat that's evolved or kicked out. And the reason is because of steps 1, 2, or 3 that we just looked at, okay? Going down going down below here, when ethanol is dissolved in hexane, it's positive 23 kilojoules per mole. So this feels cold, okay? So this one feels hot up here. Hexane feels cold when it's mixed with water, okay? Now, again, this is because ethanol is polar and hexane is very nonpolar, so very few Coulombic attractions are formed to offset the energy required to weaken the solute-solute and solvent-solvent interactions, okay? So we're going to get into why polar dissolves polar and nonpolar dissolves nonpolar, but never in between, okay? So this whole phrase between polar dissolving polar and nonpolar dissolving nonpolar is a phrase called like dissolves like, okay? But you can never go between the two. This is why oil and water don't mix. But there's energetics that are behind this, okay? And it's the energy that's actually involved here, okay? So let's go one step further. We talked about spontaneous processes. We know that exothermic or delta H's that are negative are spontaneous. So this normally happens when you dissolve ethanol with water. Now check this out. This is quite, or at least decently, positive. That's a non-spontaneous thing. So something else has to happen in order for this process to have a delta G that's negative for spontaneous processes. Okay, so we'll go a little bit further here and see if we can find something else. So heat to solution. Ideal solutions are those which with the heat of solution is zero. Okay, there's no give or take. Solutions behave most ideally when the solute and solvent are extremely similar in molecular structure and polarity. So again, let's go back to this solution, again, this statement saying that like dissolves like, okay? And now let's explore this whole thing about how the molecular structure and polarity are the same, okay? So here we have nearly ideal solutions. So we have, this is methanol, this is ethanol, and notice they both have hydrogen bonds, okay? So this is something where polar will dissolve in polar. In this particular case, this is nonpolar dissolving in nonpolar. And again, the same thing right here, nonpolar dissolving in nonpolar. Okay, so now let's take a look at this. The heat of solution for these are nearly zero because the Coulombic attractions between the solute molecules and the solvent molecules are almost identical to those between the solute and solvent molecules. Okay, so again, we don't really know which one's the solute and solvent, and the way that we would determine that is if I have perhaps 10 milliliters of this liquid and 20 milliliters of this, then this would be my solvent because I have more of it, This is the solute because I have less of it. That's how this works, believe it or not. Okay? So nearly ideal solutions are ones at which we can have almost identical polarity in Coulombic attractions. Okay, the Shihida solution can be calculated with MC delta T. We've looked at this before. I'm going to show you what this slide has. I'm not going to go too much into this because we've looked at this before. But simply, if I'm going to find delta H of solution, which is equal to Q under constant pressure, this is the mass, this is the C, and this is the delta T. Okay, very simple. This is a little bit out of order from how I do it. And we end up with a expression of 14.6 kilojoules per mole. Okay. Now, why don't oil and water mix? Again, it has to do with like dissolving like, but why doesn't like dissolve like? The answer is the energetics, or the energy that goes into these things in spontaneous processes. Okay. So what we have here is step one. You need to separate the oil particles. This is very endothermic and very easy to do because there are no LDFs here. Okay. So very few LDFs with nonpolar substances. Actually, I'm sorry, there's very few intermolecular forces, and what there are only LDFs. Excuse me, I wanted to do a little bit better on that one. Step three, notice I skipped to step three. Oil attracts water, which is exothermic. So we have a connection here. There's almost no interaction whatsoever. So again, with bond making, it's almost zero. Okay, because the two, polar and nonpolar, do not mix. So there's almost nothing here because the particles don't interact. So where I'm looking for my negative exothermic interaction here, it's almost zero. There's almost nothing here to work with. Okay. So step two says separate the water particles, which is a very endothermic thing. So again, I have something that is close to zero, something that is very endothermic. So what happens? It takes too much energy to separate the particles. This makes the whole process endothermic and very much unlikely to occur. Okay, let's take a look at a graph with this. So if we take a look at this right here, notice the ideal heats of solution is where I put in energy, and I get a ton of energy out. Okay, this is the positive side, this is the negative side. Say, exothermic processes tend to occur. Now, if I put in energy, and I don't get much energy out, so energy in, energy out. This is how delta heated solution is very endothermic. It ends up on the positive side. The solution will probably not mix or not occur. Okay, so again, it's energetics. Two considerations when we make solutions. Okay, so there's again, try to avoid the always and never. Processes that require large inputs of energy tend not to occur. That's why oil and water don't mix. However, if it requires a little energy, it can occur. Okay, so if it requires a little bit, you can do this. The second thing, and this was a little bit better here, is that processes that lead to greater disorder, in other words, increased entropy, tend to occur. So check this out. Taking table salt, which is NaCl, and dissolving it in water requires positive 3 kilojoules of energy. But because the process leads to more disorder, it tends to be favored. So if you understand delta G is equal to delta H minus T delta S, when we have, so in this case, it requires, this is a positive number here, but at room temperature, if this is quite positive as well, that means this whole term is negative, making delta G negative, and NaCl tends to work. It tends to dissolve. As we know, NaCl is quite soluble. Okay, that's it for this video. Email me with questions.